Hello. We'll be talking about some time-dependent physics today, but we first need to remind ourselves of what is called the interaction picture. So, as usual, we'll start off with the Schrodinger equation in which we have a Hamiltonian, and we'll split the Hamiltonian into two parts, H0 and H1. H0 will typically be a Hamiltonian for which we know everything we want to know about the solutions. So we might think of that as the boring part of the Hamiltonian, whereas H1 is going to be the part of the Hamiltonian that involves the really interesting dynamics. So you can think of that as the interesting part of the Hamiltonian. Using H0, we can define an operator that looks like the evolution operator, but it does not contain H1 in the exponent, so it's not the true evolution operator. And of course we'll also need the inverse of that unitary operator. So I'll also need to remind you of how we calculate derivatives of the exponential function. It's the exponential function itself multiplied by the derivative of the exponent, and apply that to U0 inverse. You get back U0 inverse multiplied by the expression in the parentheses I over h bar times H0, the boring part of the Hamiltonian. So we'll put that aside on the top corner for later use, and now consider applying this U0 inverse operator on psi as a sort of similarity transformation. Calculate the derivative of that, you get two terms. The first term is just the derivative of the U0 inverse operator, for which you will use the expression up there in the corner. And the second part is the derivative of the wave function itself. So using the expression up in the corner, you show that the derivative of U0 inverse, in fact, is just U0 inverse times minus h bar, minus H0, sorry, both of those acting on psi. And the second term, the derivative of the wave function, you just substitute from the Schrodinger equation. So that's just a full Hamiltonian acting on psi. Between the two terms, H0s cancel out, and we get a simpler looking expression, simpler looking differential equation, where we can insert between H1 and psi in the middle term, we can insert the identity, which can be conveniently written as U0 times U0 inverse, and then grouping the terms as indicated by the round parentheses. The wave function that occurs to the far left with the derivative acting on it now also occurs on the far right, and then the expression in the parentheses before that, U0 inverse H1 U0, is the operator acting on it. So we can abbreviate those, calling that operator HI, the interaction picture Hamiltonian, which in the bottom right corner is given as the similarity transform of H1, psi I, which is then the interaction picture wave function, pre-multiplied by U0 inverse, and this wave function with this operator satisfies an equation that looks exactly like the Schrodinger equation, with the exception that now the Hamiltonian focuses on just the interesting or interaction part. You can also think of this as the intermediate picture, as we'll see later, so I can stand for intermediate, interaction, or interesting, however you please. So we'll use this, but before we do that, I need to make a small remark, which is that suppose it turns out that H0 and H1 actually commute. Well, in that case, U0 also commutes with H1, because U0 is an exponential function of H0, and when expanded in a Taylor series, you can apply the commutator term by term. So then, U0 inverse H1 U0, you can compute U0 over to the left, cancel it with U0 inverse, and therefore HI is the same thing as H1. The interesting part of the Hamiltonian actually doesn't change. You can think of it also as follows. Suppose you pick a basis. In general, H1 would then turn out to be some kind of a non-trivial matrix in that basis. Well, but choose the basis in such a way that H0 acts as the same operator. Typically that's going to include the second order derivative in the kinetic term, plus maybe some potential function for a harmonic oscillator or a particle in an infinitely deep potential well or some such thing. And that operator would be acting exactly the same on each basis element, so therefore would be represented as a multiple of the identity matrix. Well then, the relationship that the commutator of H0 with H1 is 0, and that the dressed interaction picture Hamiltonian is actually the same as the H1, as noted above, can also be thought as the fact that the U0 similarity transformation cannot possibly change H0, because U0 is the exponential of H0, and it turns out that if the H0 and H1 commute, then H1 would have to be represented as a diagonal matrix to begin with, not a general non-trivial matrix. So this can be useful sometimes in visualizing how this all looks like. So we've split the Hamiltonian into H0 and H1. We've defined this operator, the unitary operator U0, used its inverse to do the similarity transformation of the wave function, and did the corresponding similarity transformation on the operator H1, the interesting part of the Hamiltonian. By the same token, we can do it on any operator R and obtain the interaction picture of that operator Ri. So then, a time derivative of such an operator Ri will end up involving three terms: the derivative of U0 inverse, the derivative of R itself, and the derivative of U0 on the far right. Using our previous formulas for the derivative of U0 inverse and of U0 by the same token, we get the first and the last term. And in the last term, knowing that U0 is an exponential of H0, we can easily commute them as indicated by the red arrow. And in the middle term, we'll just leave it as it is, but we'll swap the two terms so that with a little bit different bracketing, you can see that what's in the parentheses in the first term and the second term is what we just denoted as Ri, the interaction picture of the operator R. And once it occurs multiplied by H0 from the left, once from the right, one term is with a negative sign, the other with a positive sign, so clearly that gives you a commutator. And the last part simply gives you the similarity transformation of the time derivative of R. So you can write that as the interaction picture representation of the time derivative of R, and you obtain the general dynamical equation, how the operator Ri changes. So the rate of change of the interaction picture operator equals to the commutator, but only with H0, the boring part of the Hamiltonian, of that interaction picture representation of the operator Ri, pre-multiplied by I over H bar, plus a second term, which is the interaction picture and representation of the time derivative of the operator as given originally. Similarly, you get the Schrodinger equation, which we obtained in the previous slide, for the interaction picture wave function psi I, where in turn the dynamics is governed by Hi, the interesting part of the Hamiltonian. Notice the complementarity. While operators evolve as governed by the boring part of the Hamiltonian, the wave functions evolve governed by the interesting part of the Hamiltonian. Of course, the splitting of the Hamiltonian into the two parts H0 and H1 was up to us, so the naming boring and interesting in this case is just for easier remembering, perhaps, easier mnemonic. So putting this pair of formulas up there in the corner, look at the following special case. Suppose H0 was in fact 0. In other words, all of the Hamiltonian was interesting in our opinion. Then that unitary operator U0 would just be the identity operator. Well, with that choice, you have that the operator R, now transformed by the identity operator, of course, is unchanged. So this is what we conventionally call the Schrodinger picture, the operator given represented in the Schrodinger picture. The time derivative of the Schrodinger representation of the operator is just the time derivative of that operator as it is. And of course, the Schrodinger equation for the wave function includes all of the Hamiltonian. In other words, all of the dynamics is in the wave function. On the other hand, if you switch the definitions and make H1 0, in that case, all of the Hamiltonian is in H0, and so that U0 unitary operator is in fact the conventional evolution operator, U. In that case, the operator is transformed by the complete evolution operator as a similarity transformation. The time evolution of that operator in what's called the Heisenberg picture then contains the two terms. One of them is the commutator with the full Hamiltonian pre-multiplied by I over h bar, and the second part is the full evolution operator similarity transformation of the time derivative of the operator as given initially. And finally we have that the wave function doesn't change at all. So the wave function is static. It refers to initial or some other condition as given for the state. And all of the dynamics is contained in the evolution of the operators. So clearly then the interaction picture is an intermediate picture. And you can think of I as standing for intermediate rather than interaction. Typically we choose it so that since this interaction picture ignores any dynamics generated by H0, H0 is what is well known, and we focus on the dynamics generated by H1. So that's all for the interaction picture as a reminder, standing kind of halfway between the Schrodinger and the Heisenberg picture, and now onward to calculations. Thank you.